Good evening to all of you, those who are in the evening. For others, a good day to you. My role today is to chair this particular session of ROWS2022, where we have an eminent speaker from a premier institute in India. Dr. BASUDEV Rai joined the Department of Physics, IIT Madras during 2017, where he is now an associate professor. BASUDEV Rai received an integrated MSc in physics from IIT Kharagpur and further received MS degree in physics from the University of Maryland. He received PhD degree from the Indian Institute of Science, Education and Research in Kolkata during 2015. He has been an Alexander von Humboldt Fellow at the University of Tübingen, Germany. During 2020, he received the Department of Biotechnology Wellcome Trust India Alliance Intermediate Fellowship. His current research interests include optical tweezers and atomic physics. Without further ado, on behalf of the ROWS2022, I welcome Dr. Roy to deliver his talk entitled Study of Soft and Biological Matter System in Optical Tweezers. Over to you, Dr. Roy.
Good evening, everybody. This is BASUDEV Rai from IIT Madras. So the title of the talk is, I changed a little bit, but it's again the same thing actually, study of pitch rotations in soft matter systems using optical tweezers. So the outline of the talk essentially is the out of plane rotations in optical tweezers. I'll be describing that. I'll describe the generation of out of plane rotations with a few different ways. Then I'll go to the detection of optical tweezers, detection of the out of plane rotations. Then I'll talk about the applications and then a few other topics that I work with. Okay. So essentially, what is optical tweezers? It was developed by Professor Arthur Ashkin at that time in Bell Labs. So what he did, he was actually trying to sort of put a focused laser beam through a polystyrene sample, and he found that in 2 dimensions, it is sort of confined. It is sort of trying to pull it into the central line, while in the 3rd dimension, it's trying to kick it out. So he was actually trying to sort of balance the trap by using 2 opposing laser beams, and he found that if you now put in a second laser beam from the other side, it can actually confine it in 3 dimensions. So he published the first paper in 1970 on this thing. So here the confinement is by 2 opposing beams. So you will get confinement along the radial directions using the optical tweezers beams, and using the 2 opposing beams, you can get confinement in the axial direction. So this was the first thing he tried. After that, later on, he also showed that if you then use a very high numerical aperture lens, you can actually confine it in 3 dimensions itself, directly in the 3 dimensions, basically. So this is called, the force was known as the gradient force, because that goes as the gradient of the intensity. And this scattering force here is then tries to destabilize it out of the trap. So essentially, there are 2 competing forces. One is trying to trap it in the middle of the focal plane. The other is trying to push it out of the focal plane. So these 2 competing forces, basically, if the gradient force is large enough, what happens is it just confines it sort of slightly away from the equilibrium position, the 3-dimensional equilibrium position. So anyway, so it does. So we assume that this is sort of a harmonic potential close to the central position. So that's the one of the things. Okay. So now moving on to the specific topic of what I do, I sort of work on rotations. Most of it is on so far has been on rotations as an independent researcher. So if you have a rigid body, it can have 6 degrees of freedom. 3 of them are the translational degrees of freedom, where you have the X, Y, and Z. These are pretty well known how to detect and how to sort of generate these things. You confine it in an optical tweezers and then you move it left, right, up, down, along the axis, all that. And you can detect it pretty easily using quadrant photodiodes. You have a sort of split photodiode, and the top half minus bottom half gives you Y, the left half minus right half gives you X, and the total intensity over all 4 quadrants gives it the sort of the Z position as a kind of an interferometry from the scattered and unscattered light. Now, but that still leaves out the rotational degrees of freedom. You see, it was in 1998 that Professor Helena Rubinstein Dunlop from Australia actually showed that you can actually also sort of confine it in the, if you apply circularly polarized light, the particle also spins in the in-plane sense. Like it starts spinning like this actually. Okay, this I call the yaw motion in the nomenclature of the airlines. So it has been in existence for the past 24 years. And however, that still leaves out this other 2 degrees of freedom, the out of plane degrees of rotational freedom, the roll and the pitch. In the nomenclature of the airlines, this can be called the roll axis, this can be called the pitch axis, and this can be called the yaw axis. So the roll and the pitch are just beginning to be explored now. So I have done some work on this thing, and I'll show you what I mean by that. So essentially, the pitch degree of freedom. So I chose birefringent particles. The birefringent particles have one refractive index along one direction and another refractive index along the other 2 directions, which gives it sort of an anisotropy in the birefringents, in the refractive indices. That's called a birefringence. So that can be, you can apply a linearly polarized light, and the axis of the birefringence will align with the axis of polarization, and then you turn the polarization of this light and you will see that the particle also follows. So you can get from a dark spot to a bright spot under crossed polarizers. This is under crossed polarizers. It is a perfectly bright in 45-degree configuration, and then it goes to one of those axes. It becomes dark. However, please note that this is not perfectly dark. There are 4 lobes in here. This is what I'm going to use for my out of plane detection. So one of the first ideas I had on this was the first thing that I published basically here at IIT Madras was that I sort of did a simulation where I actually showed that this 4-lobe pattern can develop anisotropies as the particle turns in the out of plane sense, the pitch sense. So when you did that, 2 of the lobes will glow brighter, 2 of the lobes will glow dimmer. So you can find out the anisotropy in the halves, and you can sort of find out the sort of the out of plane detection. Yeah, and this is sort of a particle, the birefringent particle moving with, there is a sort of a molecular motor attached to it, a kinesin molecular motor attached to it. It's moving on a microtubule, and you can see that it is sort of, there's a very little, we sort of, earlier during my postdoc work, I had shown that it actually turns in the yaw sense, but I see that even later on in this process, there is a little bit of turn in the pitch sense also. Generally, it sort of fluctuates around sort of a mean, and it's very small fluctuations. But in general, we sort of showed that the pitch detection can be performed successfully using this kind of a configuration. So going on, I sort of developed a technique to sort of detect it using the scattered light instead of using video microscopy in the previous case where the 4 lobes were visible in the video thing. Now you can actually use the scattered light itself to sort of detect the out of plane rotation. So all I need to do is take the light, forward scattered light, and I put a sort of edge mirror and split the light into 2 halves. And the axis I have in the halves, I can find out if it is turning in that sense. So this is what I did. This is similar to this is a simulated result actually. So it's sort of almost linear here, and sort of this can be done even with the scattered light. You don't need the video camera, and that increased the speed of detection and the resolution also. So essentially, now I go into what are the generation strategies of this pitch motion. So The strategy number 1. So I have two optical tweezers beams, and this particle, this extended particle, has been trapped two beams, and one beam has been pushed in. It has been sort of, the focus has been pushed in, keeping the other focus constant. Therefore, you can see that it has turned in this sense, out of plane sense. It is clearly visible here. And this sort of, this generates the first way of detecting the pitch motion. This is a birefringent particle. It has been trapped in two different beams also, and I'll generally push the other beam in, and I'll see that it sort of develops sort of a color. The scatter pattern changes actually. You see, it's changing here. It's changing. The color is changing. It's actually, if you look into the scatter pattern, it will sort of also, the difference in halves will show you some sort of an anisotropy. So this thing was one of the sort of optical torque wrenches. You can apply control loads on this particle by sort of pushing one of the foci in. So you can turn it in a controlled sense, and you can do the detection using our scatter pattern. And then the second strategy is, you must have heard about rolling without slipping. On this is textbook stuff in high school, but have you heard about rolling without slipping at the nanoscale? Now, this is exactly what I do here. I take a polystyrene particle or birefringent particle, and then I sort of trap it very close to the surface, actually on the surface, and then I move the stage sideways. So I can see that this is generating sort of a rotational motion here. You can see that the scatter pattern is changing slightly here. And then I use my pitch detection system to sort of find out the angle by which it has turned. So when the thing is sort of following nicely, it will the x-axis is constant, while the red curve gives it the angle at which it is. So you can see it is going up and down. So this is sort of moving in one sense. It is sort of going, the angle is changing by this much, and then it's coming back again to the other position. So it is sort of, this is actually rolling without slipping. Yes. So we have also shown rolling with slipping and no rolling also using the surface properties. If you change the surface properties from hydrophilic to hydrophobic, it stops rolling. So all that. This was published in RSC Advances earlier. So the third generation strategy is, if you have a sort of gold coated surface. Generally, it was sort of, when you optically trap a particle, a hot or sort of a heated particle, or sort of like absorbing particle inside the sample chamber, which is like a glass slide here and a cover slip here, and in the middle you have the particle, then it generates convection currents. Now, nobody thought that if you take a gold layer and put it on the bottom surface, the convection currents also form very close to the surface. So we trapped, we sort of put this gold layer, and then we illuminated it with a laser beam, and then we find that this sort of this is actually a hexagonal shaped particle for now. It's actually an upconverting particle, but we are not using the upconversion properties here. We're just using it to turn it in the out of plane sense. So here the convection currents are such that it is turning here in the outer plane sense. You can clearly see that it is turning in the outer plane sense. So this was published in Biomedical Optics Express. So that's the third strategy. And then the fourth strategy, this is also actually in continuation with the third strategy. We have actually tried to sort of use polystyrene particles, and we can clearly see the convection currents going around and around. And this is a cell, a dictyostelium amoeba cell, which has been turned using this sense. It was found important enough that somebody from Texas Austin, Professor Yubing Cheng from Texas Austin, has published a follow-up paper where he has actually used this technique to sort of apply shear loads on cells, cells bound on the surfaces at the bottom. So he's applying shear forces to sort of break the bonds of this some sort of a cell attached to the surface at the there. So yeah. And then moving on to the fourth technique, this is a sort of a like the same upconverting particle, sodium yttrium fluoride, and we have this time iron doped in it as well. So this material then becomes ferromagnetic. So it will have not just optical tweezers properties, it's transparent. It also has magnetic properties. A transparent material which is magnetic is very hard to find. So that's the thing. And this can be turned in any sense, any whichever sense you prefer. This is the pitch, this is the roll. You can see the fringe is going by, so this is actually moving in the roll sense also, and this is the conventional yaw sense. It has been placed close to the surface to actually turn it in the yaw sense. So these are the 4 strategies, and then I move to the applications. The applications, this is the first application I did. Where is this useful? Where is the pitch detection useful? Actually, the pitch detection is useful where there's a dynamics change from a yaw sense. The dynamics changes when you sort of put it very close to a surface. Then this kind of a rotation will now have a different kind of dynamics as opposed to the other kind of dynamics in the yaw sense. So one of the first things I did was actually stuck this particle on top of a cell, sort of a cancer cell, breast cancer cell, MCF7. And we looked for the fluctuations of the membrane. Now I show here RBC here. RBC is red blood cells, erythrocytes. And these things also have fluctuations on the surface due to thermal fluctuations, fluctuations. So the membrane actually goes up and down, it oscillates. And that is given, it randomly happens, and it's given by the thermal fluctuations. So you can see this is the, at random instance of time, this is the RBC, and we have the differential height increase at the bottom here. So you can actually calibrate to micronewton per meter in terms of what sort of draft stiffness, the stiffness of the membrane and all that. But I used it for different purpose. I sort of put this, I sort of thought that if you have the pitch rotation happening, and if you put it on the cell membrane surface, it will detect not only the vertical fluctuations or the normal fluctuations, it will also detect the angle, sort of the slopes of the membrane can also be detected using this technique. So this detects the slope fluctuations using the rotations, the pitch rotations actually. So I'd use that. And to illustrate the point, I sort of have a video here of a cell membrane in interference reflection microscopy, where it sort of oscillates here. The membrane is flickering. You can see it has been put on a glass surface, and there's some special technique that they're using to find out this flickering. It's not happening here. So this is the membrane fluctuations, thermal fluctuations that I'm trying to detect, but this is only normal. This is vertical fluctuations, but I'm trying to sort of put 2 points next to each other. I can sort of generate a slope fluctuation also. So that I use using this birefringent particle I detected. Okay, so I do that, and I get the normal fluctuations will give me this sort of power law. The power spectral density will go as frequency sort of 1 over omega to the power of 5/3, and we get indeed 1.67 actually, 1.66 plus minus 0.4. So this is the normal fluctuations. This is conventionally well known in literature. However, the new thing that we are finding is that since this membrane is not on the glass surface, it is sort of unpinned surface. Nobody has shown that this surface will also go as a kind of a free surface. If you actually pin it, the exponent changes to 4/3. It is not 5/3 anymore, it's 4/3. So that's another domain. So I'll not talk about too much about that. Nonetheless, I will talk about the slope fluctuations here. This is the power spectral density of the slope fluctuations. It's slightly lower here. This is exponent to the 1 over omega to the power of -1. We got omega to the power of -1 here instead of 5/3, and clearly it is sort of different from the 5/3. So what happened here? So we did a theory for that, and we sort of model it as a kind of 2 points next to each other, and 1 point has been pushed up. So the slope would be given as y2 minus y1 divided by x2 minus x1, which is like the probe diameter or the contact radius. And the contact radius being constant, if the particle is sticking to the surface, the only thing you're picking up is y2 minus y1, and then you can approximate it that tan theta is theta, and then do the kind of correlation functions. This is kind of in the Fourier domain. It will be sort of the gradient of this thing, the gradient of the height fluctuations are going to give you theta, and then we can sort of use this thing to do the power spectral density, and we find it. Our colleague Manoj Gopalakrishnan in my department actually calculated this thing. And he showed that this exponent, this power spectral density is now kBt divided by 6, the bending rigidity of the membrane times omega. You can see this is omega to the power -1. I showed a little while back the data. It shows omega to the power -1. So it's kind of correct. And the slight deviation from that, it was about 1.2, and the slight deviation is because of the probe size. It's slightly it's finite size, finite resolution of the probe. So it does change a little, it deviates, but that's because of the probe radius. I went back. Sorry. Yeah. So we can directly find out the bending rigidity here. If you look at the power spectral density for the normal fluctuations, the expression, the coefficient is very complicated. It's kind of a combination of bending rigidity and cytoplasmic viscosity. Here you have a clean expression, so you can directly find out the bending rigidity. So you can simultaneously use the normal fluctuations and the slope fluctuations to find out all the parameters very cleanly, actually. So this was published in Soft Matter. And then I sort of move on to the next topic. That is the application, second application of this pitch rotation. And I sort of show here that if you take an air-water interface, a sessile droplet of water on a glass surface, and sort of take a birefringent particle to the top surface, what are the modes I can study? I can study the x direction, the z direction, and the rotational modes. I can study the rotational modes, the pitch rotation, and the all these things. So the first thing, the pitch rotation can give you this sort of a transverse mode and the horizontal shear mode. It was sort of hypothesized in 1990s that you have all these different modes in rheology of an air-water interface or sort of some interface. There are these rotational modes, there are these translational modes. The vertical compression mode is actually Z, and this compression mode gives you sort of, this is kind of X. The compression mode is X. The compression mode is X, and the shear mode gives you the yaw rotation. Actually, from the yaw rotation you can find it out. So we were the first to show that you can actually detect this using the pitch rotation. You can detect a combination of the transverse mode and the horizontal shear mode to sort of show that a sort of a pinipalm coated membrane, or kind of an air water interface coated with pinipalm, which is hydrophobic, it goes to the surface. So if you keep a certain amount of pinipalm inside a solution, it generally goes to the surface and then it builds up and becomes a membrane eventually. So it goes from a viscous, completely viscous when there is no membrane, no pinipalm on the surface. When it's completely viscous, it's the sort of the polymer viscosity. So we are using a model. This is completely viscous, and then it goes to viscoelastic because the pinipalm has now attached to the surface, and then we are going to get slightly different like behavior of the membrane. So it goes from a viscous to viscoelastic transition. We are clearly studying that. This is X, this is Z, and this is the pitch rotation that also shows a kind of a viscous to viscoelastic transition. And we can see that we can clearly study these transverse modes and the horizontal shear mode here. So this is one second application of the pitch rotation. The third application happens to be inside the cell. So we put the particle inside, the birefringent particle inside the cell. In this case, we have a particle inside an amoeba cell. You can see it is moving, and the cell has been actually held by an optical tweezers. That's why it is sort of at one spot. And sort of here there is an MCF7 cell, and you will see that this is moving slightly, all very slightly it is moving. So this is sort of optically. So this, let me play this again. This one moves. You can clearly see it is moving. That's how particles, if you put it inside a cell, it will move around. But this particle is not moving because it is actually held in optical tweezers. So we can study the rheology of these things. It has been a very complicated problem because nobody has so far been able to sort of calibrate the optical tweezers as such inside a cell. So that makes it complex to sort of finding out the viscosity and all these things inside the cell. So we had a model for this, so where we simultaneously find out the parameters for the optical tweezers from here, the draft stiffness, the viscosity of the viscoelasticity of the fluid, which is characterized by the DC viscosity time and a relaxation time, which is for the elastic part of this thing. So one DC viscosity is there and an elastic part is there. So we already did this work earlier. This was published in Journal of Physics Communication, Condensed Matter, JPCM. And using that idea here, what we are trying to do is we are comparing the rotational modes with the translational modes. How does it compare with respect to each other? That's the question. So now let's move on and let's see. Why do I ask this question? I ask this question because inside a sort of a cell, there's not just a fluid. There's also a network of actin filaments and microtubules and intermediate filaments. So there's kind of a mesh of filaments, and then there is a the fluid cytosol is there. It's sloshing back and forth. Cytosol generally has proteins dissolved in it and all kinds of things, ions and all these things are dissolved in it. And it will also have organelles, but we are not talking about organelles here. We're just talking about the cytosol here. So this is the, so if you if you move it like this, the translation, it has a different mode compared to, it has a different mode of the fibers as opposed to when you sort of put it in the rotational sense. If you stretch the fibers in a rotational sense, it will give you a different sort of viscosity, sort of rheology actually. So the parameters are different. So that was the hypothesis. Now let's see if this thing is actually matching. Let's see if that's what is happening. So we tried that experiment, and then we used a model which is sort of, as I was telling you, we have a viscoelastic model, which is kind of generalized Maxwell's model. It's not really a Maxwell's model, but there's an extra term here. It is kind of slightly a modification of the Maxwell's model. It's called the generalized Maxwell model, which we derived from the first principles, the Stokes-Waldo-Rad model. And we showed that this is actually the generalized Maxwell's model that it boils down to. And so using that, the power spectral density becomes this. So you can extract 4 parameters from here. Now, it's kind of complicated because if you fit a curve to it, von Neumann famously said that if you have 4 parameters, you can fit an elephant. And if you have 5 parameters, you can fit everything. So we have to be careful about sort of normalizing this diffusion coefficient, and then you can sort of have 3 parameters instead. You normalize to 1, and then you have 3 parameters instead. And so then you can sort of simplify your case, and you will have a better error bar. Like the error bar should be lesser. So that's the thing. We fit this model, and then we go on straight to the data set. So log block averaging gives it, so I showed that beyond like 10 hertz or something, it fits pretty well to the thermal fluctuations. Under 10 hertz is also an open question even now, because this is kind of active region. This is kind of active fluctuations happening here. So we still do not know, we don't have a model for it. We are working on it actually at the moment. And nonetheless, we have at this high frequencies, we have got thermal fluctuations, and we fit to this old, generalized Maxwell's model, and we find that it's a pretty good fit, and we can find out from there the viscosity of the system and the relaxation times, the 0 hertz viscosity of the system and the relaxation time. Because I made the viscosity frequency dependent. The parameter to compare is the 0 hertz viscosity, not any viscosity. So it has to be the 0 hertz viscosity. So that's the parameter we are comparing, and then the other parameter that we're comparing is the relaxation time. So using that, I sort of compare the translation and rotation. The translation is in the blue and the rotation is here. So it's sort of fitting well. I do not consider anything under 10 hertz because, as I said, it's the active region. It does not work very well under 10 hertz. And using that, I sort of put a kind of a sort of compared one with the other, the X viscosity ratio. This kind of viscosity ratio is with respect to water. So it is kind of giving you, given that the viscosity of water is 1 millipascal seconds, and then this is the cytosol's viscosity that we are measuring, the 0 hertz viscosity that we are measuring actually. So we are comparing the X viscosity with pitch, and we find in the range that it's between 1, which is water. 1 is water here, and this is also water here. It sort of works well between 1 and 5. It's sort of linear. After that, it starts to deviate from this thing, and it sort of shows more complex behavior, which we still do not understand actually. So we are trying to understand this thing. And the other thing is this relaxation time, the X relaxation time and the pitch relaxation time. It is sort of grouping well pretty much here. So there's not much change in the relaxation times, which is what I had expected from the this kind of polymer stretching model. It's kind of grouped actually. If you look at it on the linear plot, it will be grouped. Okay. So going on. So I also have the roll detection, a roll rotation. I also have another strategy for detecting the roll motion. You can see this is an upconverting particle which has a speck of some other particle on top. And I have two beams in one case and one beam in one case. So I just turn off the other beam periodically. And you can see it is turning. It is turning in the roll sense. It's partial roll rotation. And as you can see here, this is one beam. The configurations of this hexagonal shape has to do with that. And that if you have two beams, it is sort of like this. But if you have one beam, it is sort of like this. That changes the configuration. And we showed by numerical simulations that indeed this is the case. And this is published in Optics Express. Then we move on to another topic, another something very close to my heart. So this is subdiffractive absorption spectroscopy. You know FCS, the fluorescence correlation spectroscopy. In the fluorescence correlation spectroscopy, you know very well that you have a sort of a focused beam of light. It has been focused down very tightly using high numerical aperture lenses, and it focuses down to the diffraction limit. And then you can sort of see inside the diffraction limit if there are molecules floating by. This kind of fluorescence happening. So I sort of had the idea that what if you sort of instead of using the another extra laser beam, you have a particle which has been optically trapped at a certain wavelength, like IR wavelength, but it emits in visible radiation. It gives out visible radiation. When that happens, then you can sort of illuminate the local neighborhood of that particle using that visible radiation and can detect the absorption of that light using molecules which are in that region. So that's what we were trying to do. We find that the mode volume now sort of reduces by a lot, because if your particle is now 100 nanometers, it is already subdiffractive. It's smaller than the diffraction limit of your 1 micron beam, or even 400 nanometer blue light. It will also be sort of smaller than the diffraction limit. And in the other sense, in the other direction, you can actually do a kind of a confocaling. You can put a pinhole at the detection system, and you can detect in the very vicinity of this particle. So it gives you kind of a three-dimensional volume which is smaller than your FCS volume, conventionally accepted volume. So it's a new idea that we had. As you can see, it becomes like a dipole at that size, 100 nanometer size, and it sort of emits in 45-degree cone. It's kind of a dipole. Dipole will have its dipole emission. Dipole emission is cos square theta, so it will be 45 degrees. And while if you have kind of a focused laser beam, it will be very large. It will be of the order of 60 to 80 degrees actually. And the mode volume is also much larger than this. So we use this, and we find that indeed, if you can measure, about 100 ppm of concentration of a dye, the rhodamine B, in water using this thing. And of course, it is actually not limited by the rhodamine B concentration. It's actually limited by another thing. We are using an upconverting particle to use to generate this light. So here, this is the blue. This is the blue band. This is the green band. This rhodamine B matches pretty well with this 550 wavelength, 550 nanometer wavelength. The rhodamine B absorption is in black, but the blue thing is untouched by the rhodamine B. So it is sort of a reference peak for us. How much does it go down? Because the particle to particle, there might be some sort of a change in sizes. So that sort of a thing you want to avoid. So that's why you sort of keep it with respect to a reference. And then that reference happens to be this height of this peak and the height of the other peak in in general is it's sort of 10% error is there in that. It is slight change in the heights of these things. So that's why we can't get more precise than 100 ppm, because the sort of the error bar is that much. In the sort of ratio of these heights is about 10% at 100 ppm. So we cannot resolve any better than that. So we are working on a system where we have one particle trapped, and then you have dye molecules coming in from the side in a microfluidic chamber, and then you will have better resolutions also. So that's it. It was published in nanoscale, which is like 8.3 in fact right now. So, and then I go into another topic, assisted self-assembly at the air-water interface. So here you have an upconverting particle And then this upconverting particle is now illuminated with 975 nanometer light. As I was telling you in the previous section, it sort of emits invisible radiation. It has blue, it has green, it has red. But then it also, that means it's sort of a white light emission, but it also has the efficiency of the crystal happens to be 2%. So if you put 975 light on it, much of it is just heat. It simply heats up the local neighborhood. So we sort of put it there, and we find that in this local neighborhood there is heating, and because of that, there are convection currents generated like this. It brings in material from the sides. We can sort of make a lattice of polystyrene particles, other some extra polystyrene particles that we have in the solution, and it forms a kind of a lattice around it, hexagonal lattice here. And here we have also shown that if you take diamonds, micro diamonds, and sort of optically generate the self-assembly, and we find that the emission, we take the emission and we put it into sort of, we measure the lifetimes of these emissions of the upconverting particles at 550 nanometer particularly, because that happens to match with the diamonds also have NV centers, nitrogen vacancy centers in them, and that becomes a quantum system. And then if you sort of match the emission coming from the upconverting particle with that of the quantum system, you can have interesting effects. So what are the sorts of effects? I measure the lifetime very carefully. I find that without the NV centers or without the diamonds, it is kind of like 100-ish, 93 plus minus 8 microseconds. But if you put the diamonds in, the lifetime goes to half, 55 plus minus 5 microseconds. So why did that go down? We sort of thought about it. It seems to be a non-radiative energy transfer process into the diamond. So from the upconverting particle, it has to be the case. It's something like FRET. FRET would be molecule to molecule, or for a molecule to surface. From a molecule to a surface, it is kind of it has to be within like 30 nanometers to be sort of having an effect, interaction. So clearly that sort of a thing is happening. We still don't have a full model for this thing. We assume that this surface, the cylindrical surface is now radiating in 550 nanometers, and you have a shell of NV centers around it. So you can sort of do that, and we can find that the lifetime, the FRET process actually reduces the lifetime by a factor of 2. So we showed this is the first time that NV's absorption has been used. People generally use the NV's emission, but this is the first time the NV's absorption has been used. We have not looked at the emission on the NV's at all, because NV emissions starts at higher wavelengths than 550 nanometers. So that's the thing. And so moving on, this is the kind of reduction in the lifetime after self-assembly. So it is, the blue curve is without the sort of the NV centers or the diamonds. The red curve is with the diamonds. You can clearly see there's a kind of a reduction in this particular. This is a typical lifetime here that I showed. So it's a kind of a FRET process that we are showing here. So using, this is a kind of a new way of looking at these quantum systems. Actually, it's a kind of a new system, you can say. Okay. Moving on, I also show you one more thing. So here we have got a gold surface. I showed you that optical sort of the this upconverting particle, hexagonal shaped upconverting particle rotating in the pitch sense. Okay. Now I show you that if you have, instead of one hotspot, I put two hotspots next to each other. So what happens there? So we can also show that since this is the convection, the currents actually draw it in and it moves up. There is also a region where it actually comes down. The water also comes down because it has to form a circulation. So my idea was that if you now combine these two circulations next to each other, it will generate a kind of a two-dimensional potential. Well, the third dimension was a kind of a problem. We did not envisage what was going to happen, but we nonetheless tried it out. We find that because of thermophoresis, it actually confines it in one sense inside in the 3 dimensions. Also, there's a little bit of rotation here, but you can see there's a kind of a trap particle and sort of a cluster of these polystyrene particles, upconverting particles. Polystyrene does not trap here because of the Sorey coefficient problem. It's sort of what happens is because of thermophoresis, there's kind of a Sorey coefficient to it, and then because of the Sorey coefficient, it sort of has the third dimension is stabilized by this thermophoresis. So you can see that it is confined in all the 3 dimensions, and you can move it from one side to the other if you want. Okay. So this is kind of one of the traps I have. And then I also talk about briefly about the hot Brownian motion. So what is it, hot Brownian motion? A hot Brownian motion typically has the same upconverting particle. If I now illuminate with 975, as I said, there's a kind of a heat generated, a lot of heat generated. What happens is it emits preferentially in the backscatter direction. So there's more heat generated in the backscatter direction than the forward scatter direction. So what does that do? You have the particles on one side of the particle, there is a hot spot. On the other side, there's a cold spot. On the top, there is a cold spot. So it kind of generates a kind of push from the bottom to the top. So it becomes an active system now. So by the Sorey coefficient, again, you can sort of, this hot Brownian motion implies that you will have a velocity directed upwards. And we show that this kind of, the time series shows this kind of skewedness in one side. The probability distribution function is skewed in one side. And the at lower powers, it sort of becomes more symmetric, but at higher powers, you can clearly see it is asymmetric. So it pushes up. Okay, so using this, we thought of making a heat engine actually. Before going into that, I'll show you this MSD, the mean square displacement. This is kind of the same upconverting particle trapped with slightly different wavelength, the 1064 nanometers. It is kind of diffusive here. However, the moment you go to 975, where that emission happens, that the emission wavelength, this is the pump wavelength of upconverting particles. At that pump wavelength, the MSD now becomes like this, quadratic kind of a thing. It's more complicated. It's kind of given by the active system kind of MSD. So we fit it and we find the velocities out. It's like 35 nanometers per second, or even lower than that sometimes. So then I had the idea of using it to sort of make a Stirling engine. So yeah, this is the kind of MSD here. This is the full expression for MSD here. And then in the next one, I sort of use it to make a Stirling engine. So what do? I have in the Stirling engine, there are 4 legs. There's an isothermal compression leg. There's an isochoric heating leg. There's another isothermal expansion leg, and a kind of an isochoric cooling leg. To generate the isothermal compression, I simply increase the trap stiffness so the particles expansion volume is lesser. And then in the isochoric heating part, the trap stiffness is held constant, but the activity is now changed. The activity is increased. In the isothermal expansion, again, the trap stiffness is now reduced so that the potential well is now more relaxed. And in the isochoric cooling part, the activity is now reduced, keeping the trap stiffness constant. So these are the 4 legs of the Stirling engine. So what I do here is then, how do I generate this kind of an isothermal compression? Compression is easy, you just increase the trap stiffness. However, this isochoric heating part has a bit of trick. You see, in 975, you get this activity, this velocity I talked about in the previous slide. Now, if you then, but then that also changes the trap stiffness of the optical tweezers. So I combine 2 laser beams together, one at 1064, one at 975. I sort of increase the trap stiffness of 975 while reducing the trap stiffness of 1064 to keep the total intensity at the hotspot constant. So that gives it the sort of the activity is changing, but the trap stiffness is constant. That sort of a thing. Okay, so this is what I do here. In this leg, the 1064 is increasing to increase the trap stiffness. This is almost constant here. The 975. Then the 975 goes up. The 1064 reduces to keep the trap stiffness constant, while the activity goes up. And then you have the 975 trap stiffness power constant. Here, the 1064 power is going down to generate this isothermal expansion. And in the last leg, again, the 975 goes up while the 1064, so 975 goes down and the 1064 goes up to keep the total power constant again. So these are the results. You have in this leg, this is the isothermal compression leg. The trap stiffness goes up and the velocity, the active velocity remains almost constant. Here in the next leg, the isochoric heating leg, the velocity then increases while the trap stiffness is constant. In the third leg, the velocity is constant and the trap stiffness is reduced. In the fourth leg, the trap stiffness is constant while the velocity is changing, it's reducing actually. These are the 4 legs, and if I make a trap stiffness versus velocity diagram, I can clearly see a cycle here. There's one cycle here. So we are working on this, we'll be developing it more further. So this is kind of a Stirling engine that we have developed using these things. So yeah, and this pitch rotation work was found interesting enough that we were asked to write in the roadmap for optical tweezers that is going to be that is under review. It's going to be coming out soon enough. Actually, it's almost got favorable reviews. The entire community of optical tweezers has written. I wrote particularly about generation and measurement of torques, particularly out of plane torques. And yeah, it is going to come out soon, so you can actually take a look later on. So this is the thing. And so this is my group, the students. I think this is not so important. And yeah, so I leave you with this new system that we have put in here. Is an external phase contrast microscope. So if you take a dictyostelium cell and put it in bright field here, this will inside the cell nothing is visible. There's almost nothing visible. However, if you take this same dictyostelium cell and put it under external phase contrast microscopy, it sort of shows all this small lipid droplets moving around, the globules moving around. So this is kind of, we have an external phase contrast system where the phase contrast ring is not sitting on the objective, it's sitting somewhere else, and we detect it with slightly different technology. This is a Nikon microscope. This is the state of the art that Nikon can do. We have the best objectives you have. So yeah, thank you.